Today we will start our lecture with the root test. Let me state what the root test is. We observe the term and we think about the limit of nth root of absolute value of an, and if that converges L, and if that is less than 1, then summation n equals 1 to infinity, an is absolutely convergent. So absolute convergence means when you think about the summation of absolute value of an, the series still converges. That also implies the series converges. The second one is if limit n goes to infinity, nth root of absolute value of an equals L that is greater than 1, or if that diverges to infinity, then the series diverges. It is not about it, the series doesn't converge absolutely. The last one is about the statement about the inconclusive test. When we take nth root of absolute value of an, if that converges 1, then the root test is inconclusive. What you can imagine by looking at the statement of the root test is maybe it'll be convenient if the each term of the series is raised to the nth power. Then by taking nth root of each term, we can simplify the terms and we can think about the limit easily to determine whether the given series converges or diverges. Let's go through some examples. Use the root test to determine whether the series converges or diverges. The first one is n equals 1 to infinity, n squared plus 5 over 3n squared plus 4 to the n power. So we can see this n power, and so we imagine that the root test will be pretty convenient. So n squared plus 5 over 3n squared plus 4 to the n power. So nth root of absolute value of an equals, so n squared plus 5 over 3n squared plus 4 to the n power. And we think about 1 over nth power. And then those will cancel each other. And we have n squared plus 5 over 3n squared plus 4. So limit n goes to infinity, nth root of absolute value of an equals limit n goes to infinity. We already obtained n squared plus 5 over 3n squared plus 4. So we can ignore this minor part, and then we have the same limit n goes to infinity, n squared over 3n squared. So that equals 1/3, which is less than 1. So what we can say is, based on the absolute convergent test, the given series n equals 1 to infinity, n squared plus 5 over 3n squared plus 4 to the n converges. Absolutely. The next problem is similar pattern. Each term is raised to the certain power. We consider summation n equals 2 to infinity 3n over n plus 1 to the 3n power. So in this case, each term is defined by this one. So minus 3n over n plus 1 to the 3n power. And we want to apply the root test. And so limit n goes to infinity, nth root of absolute value of an. So that equals limit n goes to infinity. So minus 3n over n plus 1 to the 3n power to the 1 over n. So by using the power rule, we have to think about this power and simplify first. So do n cancel each other. So we have, we just forget minus here because we are thinking about absolute value. So n over n plus 1 cubed. So 3n. So this number, so we can just think about the simpler version. And then we can ignore this 1 because 1 is tiny when n is extremely huge. So the limit of this one is the same as 3n over n cubed. So that is limit n goes to infinity, 3 cubed, which is 27, which is greater than 1. So the series diverges. By the root test. Let's do one more example with the root test. The next one is n equals 3 to infinity, 4 times 1 plus 1 over n to the n squared. So an is 4 times 1 plus 1 over n to the n squared. So we consider n goes to infinity, nth root of absolute value of an. Then that equals limit n goes to infinity. Just an. So that is 4 times 1 plus 1 over n to the n squared to the 1 over n power. So we can do something like this. N goes to infinity. We just split that to each factor. Then that becomes 4 to the 1 over n times 1 plus 1 over n to the n squared times 1 over n. So limit n goes to infinity, 4 to the 1 over n power times limit n goes to infinity. These two will cancel each other. So we have 1 plus 1 over n to the n power. So n goes to infinity, then this power will go to 0. So the limit is 4 to the 0 times this part. We already know this is the definition of E. So this is 1 times E equals E. E is 2 point something, and so that is greater than 1. Therefore, the series diverges. That's it for this section. 11.7 is about the strategy for testing series. We combine all of those and just we are throwing a random type of question, and we have to decide which convergence test we have to apply. This time, the problem is not suggesting you what particular test do you have to use. Test the series for convergence or divergence. The first question is summation n equals 1 to infinity, 8n plus 1 to the n power over n to the 5n power. So if you look at this, then there are nth power to the numerator and the denominator. So it's easily, you can say easily that you have to use the root test. So we consider limit n goes to infinity. The given fraction is 8n plus 1 to the n power over n to the 5n power to the 1 over n power. So that becomes limit n goes to infinity. So we are thinking about n equals 1 to infinity, so we can forget the absolute value sign. So 8n plus 1 to the n power to the 1 over n power, n to the 5n, and 1 over n power. So limit n goes to infinity. Those will cancel each other. So the numerator becomes 8n plus 1 over denominator is n to the 5th power. So obviously the denominator's degree is bigger than the numerator's degree. So the limit goes to 0, which is less than 1. So the series converges absolutely by the root test. Next problem is summation n equals 1 to infinity, n squared times 7 to the n minus 1 power over negative 9 to the n power. If you look at the pattern, then the first thing you may notice is there's n minus 1 power, there's n power. So you may wonder whether the root test is the best test to apply. But unfortunately, we have n squared. So the other test you can consider is the ratio test. If you think about the ratio between the consecutive terms, then this part will become just a number. So let's do that. Limit n goes to infinity. Absolute value of an plus 1 over an. And then that equals n goes to infinity. An plus 1 times 1 over an, right? And so that equals limit n goes to infinity. Absolute value of an plus 1. So n plus 1 squared times 7, n plus 1 minus 1 over minus 9 to the n plus 1. And then 1 over an, so we just flip it, then that becomes 9 minus 9 to the n power over n squared times 7 to the n minus 1 power. So that equals limit n goes to infinity. Absolute value, let's just gather the same kind of things. I will put these in the same fraction. So n plus 1 squared over n squared times this becomes 7 to the n power, and I will gather with this one 7 to the n power over 7 to the n minus 1 power. And we think about these two, then that is negative 9 to the n power over negative 9 to the n plus 1 power. So we will simplify a little bit, then that is limit n goes to infinity. So first one, we can combine those n plus 1 over n squared times this one, the difference in power is 1, and the numerator has higher power, so that becomes 7 times, in this case, again, the difference is 1, but denominator has higher power, so it becomes 1 over negative 9. So we can forget negative 9 here, and we just think about n goes to infinity, and we forget the absolute value sign. Then we have n plus 1 over n squared times 7 over 9. We combine these two. So as n goes to infinity, we can forget this part. And so that becomes 1 times 7 over 9, which is 7 over 9, which is less than 1. So we can say that the series converges by the ratio test. Indeed, in this case, the series converges absolutely, but they're asking whether the series converges or diverges. The next problem is summation k equals 1 to infinity 4 to the k power times k factorial over k plus 2 factorial. So of course, we cannot use the root test because of the factorial related thing. So we still want to use the ratio test. Limit n goes to infinity, absolute value of an plus 1 over an. Then again, we split the fraction into an plus 1 times 1 over an. So that is limit n goes to infinity. We can just forget the absolute value because k starts from 1. So an plus 1 is 4 to the k plus 1 times k plus 1 factorial over k plus 1 plus 2 will make k plus 3 factorial times 1 over n. We have to flip this fraction. So we have k plus 2 factorial over 4 to the k power times k factorial. So actually I had to write k because we were using k. Let's gather the same kind together. Limit k goes to infinity, 4 to the k plus 1 over 4 to the k. So I am combining these two. And I will combine these two. Then k plus 1 factorial over k factorial times k plus 2 factorial over k plus 3 factorial digit 2. So when we simplify the first part of the fraction, we get 4, right? K plus 1 minus k. And then for this one, let's just write down. So k plus 1 times k minus 1 times 2 times 1. And then k factorial is k times k minus 1, 2 times 1. And the next one is k plus 2 times k plus 1, 2 times 1. And this one is k plus 3, k plus 2, and k plus 1, 2 times 1. And so what it essentially say is just all those things will cancel each other. So these will cancel each other. So what we get is limit k goes to infinity for k plus 1 over k plus 3. So that is we pull out 4 here, and then limit k goes to infinity k plus 1 over k plus 3. So when we think about this limit, we can forget this part, and then we have 1, right? Fraction 1. So that is 4 times 1, which is 4. That is greater than 1. So what we are seeing is by the ratio test, the series diverges. Let's do the next problem. So summation n equals 1 to infinity, sine of 4n over 1 plus 9 to the n power. So from here, what you notice is this sine function is a bounded function. So that is less than or equal to 1. So maybe it is better to compare with the sequence, which is 1 over 1 plus 9 to the n power. So let's do our reasoning in such way. Sine of 4n over sine of 4n over 1 plus 9 to the n power. When we think about the absolute value, that is less than or equal to 1 over 1 plus 9 to the n power. Here, sine of x, absolute value of sine of x is less than or equal to 1. And then what we can compare here is 1 over 9 to the n power. So because 1 plus 9 to the n power is larger, and so 1 over something is smaller. So this one is 1 over 9 to the n power. And what we know is when we think about the series formed by this sequence 1/9 to the n power, that is geometric series with the ratio less than 1. And then that converges. As I said, that's because the ratio is less than 1. So what we are applying is the comparison test. So given series summation n equals 1 to infinity, absolute value of sine of 4n over 1 plus 9 to the n power converges by the comparison test. So that means the series converges absolutely. Let's do other problem. N equals 1 to infinity, n to the 4th power plus 1 over n to the 5th power plus 1. So in this case, obviously, we cannot use absolute the root test because n is not raised to the power. And if you try to use the ratio test, then because of this plus 1, things will become harder. So we will not use the ratio test. And we can think about the comparison test. But unfortunately, if we just forget this part, then comparison test is possible. And also, if you just separate that into 2 parts, then comparison test is still possible. However, separating that into 2 terms is not very convenient. So what we will do will be we will use the limit comparison test. So the given sequence an is n to the 4th power over plus 1 over n to the 5th power plus 1. And the other sequence is 1 over n. So when we think about the limit, we just forget this part and simplify, and then we got 1 over n, right? And so what we can imagine is when we think about the ratio between an and bn, the limit will approach 1. And then that means both converges or both diverges. So we consider limit n goes to infinity, an over bn. So we will rewrite that as limit n goes to infinity, an times 1 over bn. That means n goes to infinity, an is n to the 4th power plus 1 over n to the 5th power plus 1 times 1 over bn is n over 1, just flip it. So that becomes limit n goes to infinity. We distribute, then that is n to the fifth power plus n over n to the fifth power plus 1. I said you can just ignore the lower degree term and you just think about the highest degree term. And then that is limit n to the fifth power over n to the fifth power. And so that is limit 1, right? So what is a little bit confusing is when it becomes 1 in the root test or ratio test, that the test become inconclusive. But we are applying the limit comparison test. When we apply limit comparison test, if the limit turn out to be finite and positive number, then both converges or both diverges. In this case, we are comparing with the harmonic series. So harmonic series diverges. So this series also diverges. So summation n equals 1 to infinity, 1 over n diverges. Therefore, n equals 1 to infinity, n to the fourth power plus 1 over n to the fifth power plus 1 diverges by the limit comparison test. Let's do one more problem for today. The next problem is summation n equals 1 to infinity 4n factorial over e to the n squared. So obviously the only way to go is just the ratio test for this case. So we think about an plus 1 over an, and then that equals limit n goes to infinity. We can forget absolute value because everything is positive. An plus 1 times 1 over an. So limit n goes to infinity, an plus 1 is 4 times n plus 1 factorial over e to the n plus 1 squared times an. 1 over an, just to flip it, e to the n squared over 4n factorial. So we have to expand n plus 1 squared, then we get n squared plus 2 times ab, which is n plus 1. So we will write it down. Limit n goes to infinity for n plus 1 factorial over e to the n squared plus 2n plus 1 times e to the n squared over 4n factorial. So these 4 will cancel each other, and we will gather the same kind. So limit n goes to infinity, n plus 1 factorial over n factorial times e to the n squared over e to the n squared plus 2n plus 1. So we will do something similar we have been doing. N goes to infinity, n plus 1 factorial will be n plus 1 times n minus 1 times 2 times 1 over n factorial is n times n minus 1, 2 times 1. And then the numerator is e to the n squared over denominator is e to the n squared times e to the 2n plus 1. So we just split that. So these two will cancel each other, and then these two will cancel each other. So limit n goes to infinity, n plus 1 over e to the 2n plus 1 power. So of course, if you think about the pattern of growth, and then this goes a lot the grows a lot faster. So the limit would obviously approach 0, but we can apply the L'Hopital's rule for rigor. So if you differentiate the numerator, then that is 1, and the denominator e to the 2n plus 1 times the chain rule 2n plus 1, derivative of 2n plus 1 is 2. So that equals 0 because exponential function goes up like this. So that is less than 1. That means the series converges. Any question? The next question is relatively longer, which uses integration, and so I will do it next week. If you have question, then you can ask me question. Otherwise, you can leave.